Right, in this unit standard, we'll be looking at analyze and define information systems, where we look at information's role, risk, the development life cycle, and databases. So, information shapes the organization. Before designing a system, you must see why information matters. Information isn't just stored data, it's what an organization uses to control itself and shape how people behave. So, there's obviously the idea of information versus data. Data is raw facts, that is a number, such as a list of your names and your weights and so forth, while information is data given meaning and context. That number is the month's sales down 10%. So we know that sales, but it's showing that the sales have actually gone down by 10%. That has now since been analyzed and giving you back the output that you need. So systems exist to turn data into information. Now, when we talk about control, we talk about managers who use information to monitor performance and steer the organization, like a dashboard steers the driver. Behavior then is what you measure changes that people do. So, for example, staff focus on the targets the information system reports. So once you are able to see what people are doing, you are able to actually take action upon that. That then changes the behavior on how you do your marketing, your reporting, and so forth. Coordination then comes in with shared information that aligns teams, so departments are not working against each other. So we need to work as a team, and there has to be some cohesion between the two or more departments that we have. Then we have culture and motivation, which is transparent, timely information, then builds trust and engagement. Hidden or late information breeds the opposite. So once there's no transparency, obviously people will not be happy. For example, a call center showing agents a live dashboard of their resolved call count, the information itself nudges behavior, it lifts performance for better or worse if the metric is wrong. Okay, so obviously now you know exactly how maybe your other colleagues are behaving, how much they are able to do in a day, and you're only able to do half. That then motivates you to learn better, to be faster, to be more efficient. In plain terms, information is the scoreboard at a rugby match. It doesn't just record the game, it changes how the players play. All right. Then, under this, we then look at risks relating to information. Designing systems means designing for what can go wrong. Information risks come in 4 flavors. Keep them separate because each needs a different defense. We have economic risk, which is financial loss from breaches, intellectual property theft, or the cost of security itself. We have technical risk, which is cyber attacks, system failures, and obsolescence, which is literally technology becoming updated. All this is about technology, not the money itself. We also have operational risk, which is day-to-day breakdowns, poor data quality, process disruptions, and human error during normal running. This is another big risk where the human input in your systems could actually bring the whole systems to a halt. Then we also have behavioral risk, which is people problems, which is insider threats, where trusted staff misuse access, where we have corrupt agents, especially in our large organizations in South Africa. Or we could also have resistance to change. We might be with a good idea to update to the latest technologies and so forth, but the people who have been with the company for a long actually do not like the new system, and they would rather we keep the old, outdated system. And also, we could also have low security awareness, where people still allow each other to do things such as tailgating, which also is related to our cultures. Obviously, we are used to having to hold the door for someone to come through, but with today's cybersecurity space, we need to let each person sign in with their own tags or with their own fingerprints, obviously to reduce the risk of people misusing their privilege that they've been given by someone holding the door for them, and therefore letting them sometimes be able to enter into restricted areas. So behavior is a big risk in the information age. And then why do we need to split them? it's because we have to approach them differently. A firewall stops a technical risk but does nothing for a behavioral insider threat. A firewall, remember, is literally a software that is set up to literally allow certain traffic via the internet, such as going to certain websites, and also deny certain traffic via the internet, such as going to other types of websites. Certain companies even go as far as to totally deny access to any social media websites during work hours, obviously to promote productivity. So this is totally different from behavioral insider threats, which it literally goes on to be literally about in as much as you could have denied certain websites to be accessed. But for administrators, that that would not be the fact, because they're the ones who literally are able to deny these particular things. So if an administrator suddenly upgrades other accounts to administrator account, it means all the security measures that are in place would not be working as they were designed to do, because now even people who are not administrators have got administrator privilege when they are using the system, which is a behavioral insider threat. This could be done by someone trying to look cool to their colleagues. This could also even be done by someone trying to gain favor with a certain colleague for whatever reasons that they might have. This is a behavioral threat, and there's nothing that a firewall can do against this, because a firewall only works according to the type of account that the person has been able to log in with. So mixing them, meaning mixing any type of these particular threats, would actually end up hiding the real gaps and leaving us very vulnerable. An example we can have is a bank faces a phishing attack, which is technical, that then succeeds only because a teller clicks the links, which is behavioral, and then the breach then becomes an economic loss. So these are three distinct risks, and they have three different fixes. The phishing attack is technical, sends an email, and the teller then clicks on that, which is behavioral, that then makes the whole thing then an economic risk. So looking at them separately, then uniting all of them, then helps us to make sure that we don't leave any stone unturned in finding our solutions. In plain terms, like protecting a house, a strong lock, technical, is useless if a resident hands over the key, which is behavioral, or can't afford an alarm, which is economic. All right. Now, let us look at techniques and management theories. This is how systems are built. This now talks about how the fact that how systems are built keeps evolving. So how we used to build systems before is no longer the same way now. So new techniques and management theories reshape the development life cycle. So knowing them lets you advise an organization on better ways to work. Let's look at Agile and DevOps. This is iterative. We've already discussed this at length before, where we are looking at customer-focused delivery, which is Agile, which is extended into continuous automated releases, which is then DevOps, the development and operations working at once. So these are the techniques that we are then able to manage our systems and manage our projects so that we do what is right by our clients. There's also lean development, which cut wastes and maximizes value, which is borrowed from the manufacturing, especially from Toyota, and it's focused on flow, not on the paperwork. Then there's rapid application development, or RAD, which build quick prototypes and refine using user feedback, unlike slow upfront design. So instead of us having to worry too much about the descriptions and the technicalities behind the descriptions and so forth, we literally just quickly give an example and show it. This could be then a mock example for the website would look. The client then appreciates it. We continue. If they don't, we then drop that and choose whatever they would want. This then makes us faster. There's also the theory of constraints, or TOC, which is find and fix the single biggest bottleneck, which is because that's what that's what limits the whole system. So once you see the whole system being delayed by a certain thing, maybe it's a certain supplier in your supply chain, this can then make you be able to maybe replace them with a better supplier, and then that fixes the whole problem of your supply chain being delayed. Then there's also total quality management, or TQM, and Six Sigma, where total quality management builds quality into every step, and Six Sigma uses data to drive defects towards zero. All these are different management theories that are described much further in your learner guide if you need to go deeper into them. But for your exam, for your assessments, a lot of what we're discussing here will be able to be enough. Then an example is a South African insurer adopting Agile and DevOps to release updates weekly instead of twice a year, while using Six Sigma to cut claim processing errors. So all these techniques can actually be used in conjunction with each other so that you can get both benefits of all of them and be able to deliver on your promise. In plain terms, these theories are different training regimes for the same athlete. Each promises a fitter, faster development process in its own way. So there's no way of saying one could be better than the other. The best is just to know that each one of them is able to give you the results that you need. It's just about context and knowing what it is dedicated to do so that you don't end up with problems. The idea of Lean and Six Sigma are factory floor ideas. Lean is from Toyota's production system. The term was coined in the Massachusetts Institute of Technology in 1988, while Six Sigma is from Motorola, which was done in 1986. Sigma is the statistics symbol for variation, and Six Sigma just means 3.4 defects per million when you statistically then run that through the mathematical equations and so forth. So all these are then used to make sure that we end up with the best way to run our systems than before. Then we've got the systems development life cycle. Every information system is born, built, used, and rebuilt and retired, through a structured path. The systems development life cycle, or SDLC, is that path, and each phase carries its own project management work and documents. So these are the phases that you go through. Sometimes this can be expanded to be more phases than these phases. Now you have sub phases and so forth. But for simplicity, we'll look at them from planning and analysis to design to development and testing to implementation, and then lastly maintenance. In planning and analysis, you are looking at planning, at setting the scope, the goals, and resources. So analysis then studies and documents what the system must actually do. These are two distinct phases, not one. So you plan, you analyze, then you move on to your design, which turn requirements into an architecture and specification, the blueprint before any code. And then development as testing is this development builds this particular system that you want to do, while testing then verifies that it works and is safe. Building and checking are deliberately separate. And then implementation is you deploying to users using one of the rollout strategies from the other unit standard that we looked at, to say, how are we going to roll out? Is this going to be fast? Is this going to be a big bang? And so forth. All that then depends on context. And then obviously we have maintenance. Not all systems are never perfect. So we need to support, to fix, and improve after we go live. Usually this is the longest and most expensive phase, because there are certain mistakes that can then be discovered on the field, and solving them could actually mean us compensating people who have lost their money because of using our system, which is something that is sometimes very costly and difficult to actually even implement. An example will be the Home Affairs building, a new identity system. So months of analysis and design, a controlled build and test, a first implementation, then years of maintenance as laws and volumes change. Okay, so in plain terms, we mean like building and running a restaurant. Plan the concept, design the kitchen, fit it out, trial run the menu, open the doors, then keep it running day after day. If you skip some of these phases, you might then discover when people start getting sick that your restaurant is not really upholding the best health requirements, and that might require you having to answer in a court of law and compensate for all those people whose health was put at risk. You wouldn't want to do that. So why is it called the system development life cycle, you might wonder. This idea grew out of the 1960s systems engineering. This is borrowing from the word life cycle from biology. A system is treated like a living thing that is conceived, that grows, that matures, and that eventually gets retired and replaced, just like all of us. Just got me thinking. Then we also have the idea of databases and database management systems. In this day and age, we can't talk of information without talking about databases, because that's where all the data is actually stored for us to process and get the information in the first place. So information systems live or die on their data store. A database holds the data. A database management system, DBMS, is the software that governs how that data is organized, reached, and protected. We have the idea of a database versus DBMS. The database is the stored data. Okay, the DBMS or database management system, for example, Microsoft SQL Server or MySQL, is the engine that organizes, secures, and serves it. So database is the data itself. The engine that then source that data and make it make sense is then the database management system. Don't confuse the container with the contains. The container is the database. And then the management of the contents is then done by the DBMS. We also have the idea of flat versus relational. A flat database is a single table of rows. A relational database links many related tables, avoiding duplication. Okay, so a flat database could be literally where you store all the list of your groceries in one Excel spreadsheet, while a relational database will literally be having a lot of tables in your spreadsheets and then linking them to each other, finding relationships based upon, for example, the customer ID and so forth. Once they are related, tables are relating to each other, it then becomes a relational database. Each one has got its own uses. Flat databases are very useful for small projects, while relational databases are literally the driver behind all what we have nowadays, like your social media, your video platforms, and so forth. We also have the idea of acquisition and storage. Acquisition is how data is captured into the system and held securely and efficiently. So we acquire the data and store it efficiently. And then there's also the idea of access and sharing, which is retrieving data with the right permissions and letting many users work on the same data safely, which is where now cloud computing, for example, really shines, where we all have a centralized view of our data and everyone has got access according to their authentified users and so forth, and then the rest is history. We also have the idea of control, where we are maintaining integrity, where data stays correct, security and consistency. We also have security and consistency, and backing it up is then there so that it survives in terms of failures. So we could have one of the servers that then break down. If we have a backup, we can then just go to the backup server and continuing. An example would be Capitex banking app. Millions of transactions sit in a relational database, with the database management system enforcing that no two people withdraw the same account at the same moment. So obviously that would mean that there is another person who's using your account. So now we have to block both of them and then identify the real one by having them come to one of our branches and identifying themselves. In plain terms, the database is the library's books. The database management system is the librarian who shelves them. So they are able to shelve them, find them, controls who borrows what, and keeps a backup catalog. Why is it called this, you might ask? The language for relational databases began at IBM in 1974 as SQL, or Structured English Query Language. It was shortened to Structured Query Language, and that's why up to now you hear a lot of people still referring to it as SQL, even if it's just SQL. Then this was then done, obviously, because there was a trademark clash with a British aircraft firm already using the word SQL. All right. Then we have the analysis and design for future structure. So a good design fits the organization, not just the task. So you study how the organization is shaped and pick analysis and design techniques that suit it. This goes hand in line with system analysis, which is studying how the current system and processes work and what's needed, and then understanding the problem before actually doing the designing itself. System design is modeling the new system to meet those requirements, and it is distinct from analysis because this is actually creating the solution itself. Hierarchical structure. This is clear layers and top-down reporting. It suits formal documented design with sign-offs at each level. So flat structure then has fewer layers for collaborative decisions and suits agile and lightweight design. And then we also could have a matrix structure, which is staff report two ways, to a function and to a project. So suits cross-functional projects but needs careful coordination. So this is how you can literally then be able to analyze and design for the structure of your projects. Now, an example would be designing a system for a big bank, which is hierarchical, means formal approvals at each layer. The same exercise for a small Cape Town agents could be flat, which means quick workshop and a shared whiteboard and everything is fine. So solutions are never one size fits all. For different contexts, we then use different ways of approach, from the hierarchical structure to the flat structure to the matrix structure. All of them are suitable for their own particular use cases. In plain terms, you tailor a suit to the body wearing it. Analysis takes the measurements, design cuts the clothes to fit the specific organization. That's it about this unit standard. Let's meet each other on the next one, which is the designing inputs and outputs.